Thank you very much for the invitation. Thank you very much. I thank the organizer for this opportunity to be here, to be producing new papers in 1 week. Let's see what we will be able to do. Yes. So I'm going to. My talk is designed to speak about looking specifically for concrete paths of diffusion and how to find them in a geometric way, and to speak about times of diffusion, the epsilon that is needed. Not today because I was not able to finish. I don't have good numerical experiments about the amount of orbits that diffuse, but this is something that I can tell you in private during all the week. Anyway, this is a joint work with Rodrigo, and so I'm going to speak about Arnold diffusion. I think that all of you know about this, and so you can also complain because for you, I don't know if we will or not Arnold diffusion, and what is a complete family of perturbation. Okay, good. So I like to begin always with the result. Okay, without saying anything, and from this on, I will try to explain what is happening here. So this, I will speak about 2.5 degrees of freedom, 3.5 degrees of freedom, but I will be concentrating mainly on 2.5 degrees of freedom. So I mean, I am in what is called a priori unstable system, so I will recall this to all of you. So this means I have a pendulum, have a rotor, and some perturbation. This is pretty standard. I mean, this perturbation is a little bit is not too complicated. Because first it only depends on the angles, so but this is something like classical, and it has some form in such a way that it makes easy to compute some Malikov potential. So this is not really I mean necessary, but this makes things easier. So there is a product here that depends on some function depends on Q. It is chosen in this way, but it can be whatever. For the experts, I mean, depending on if you put more harmonics, when you compute this some Malikov potential, you will have poles of higher order, so it will be more complicated, but this is not a problem. It is special because some normally hyperbolic invariant manifold will be preserved, but if not, it's not also a problem because you can compute up to first order how it can be moved. But the important thing is that it depends on some angles, phi and s. Phi is the angle conjugated to the action, and s is the time. And what I'm saying here is that I'm putting two arbitrary harmonics. Okay? And so the only thing that I am requiring here, and these two harmonics to be independent. Okay? And these A1 and A2, both of them different from 0. And so I will recall in a moment that if some of this fails, it is impossible to have any kind of diffusion. So this is totally necessary. And so a part of this is totally general. So this is what I call complete, or maybe I should have put another name. But anyway, then the result is that for any I star, whatever you like, there exists an epsilon depending on I star A1, A2. If you want, I will try to be as computative as possible, as concrete, so I can give also estimates about this, okay? In such a way that the epsilon is small, so it's greater than 0, small, that this is epsilon star, there is a trajectory that for some time, so at the beginning it is smaller than minus I star, at the end is greater or equal to this I star for some time. And I also will give estimates of time, okay? All this will be concrete. So, as you know very well, the important thing here is when epsilon is equal to 0, the I is constant. And what I'm saying here, even if epsilon is 10 to the minus 10, there will be an orbit that will go from minus I star to I star, whatever it is, but maybe the time will be very large, okay? So I owe you, for the moment, estimates about the time, about the epsilon, okay? but all this can be computed. And so the nice thing is that for any value of this A1, A2, whatever you put, as long as they are not 0, and in A2 harmonics, this happens. So what I'm going to do is to speak about the scattering maps. All this is related to, I will construct the scattering maps, I will compute them, I will try to show you how many of them we have, which one are the useful, which one are the ones that can produce diffusion with more speed or not, etc., etc. And combining several scattering maps or several scattering maps of something that is called the inner dynamics, it will be possible to detect global instability. And all of this is, of course, is based in some previous work that in fact began in the last millennium in Minneapolis with Rafa and Tere. And so we will compute these scattering maps here and estimate the time of diffusion. In some cases, the only problem here is that I will have to play with this parameter, with all the value of the parameter, to see that this also always possible. I will show you what are the bifurcation of the scattering maps, no? Because sometimes there are some tangencies that appear, so they appear more. And I'm going to tell you also what happens a little bit in the case of 3.5 degrees of freedom, although I will not be able to give so many details because this is a totally work that is totally in progress. Good. First of all, it is very easy to check that if instead of 2 harmonics you have only one, so one is multiple of the other, of if one of these two, A1 or A2 is equal to 0, there is no global instability. And the thing is that you, after some change, you know that you have a Hamiltonian of 2 degrees of freedom and not 2.5. Okay, so this is very easy to see. And so now, when you consider this arbitrary two perturbations, that in principle it appears here, oh, that this is very general because you can have a lot of K1 and L1, etc., making some change of in the parameters. In the end, you can see that there are only two that are the two different ones. There are 2 cases that I mean, making change in the angles. You can see that you can reduce all the possible perturbation to these 2 cases. The first case is that the G depends only on phi and S, and and here there appears the phi, here appears the S, so they are totally uncoupled. And the other case is that here appears phi, but here also appears the phi, and this is the other case, and we will see that this has some influence in the inner dynamics. Okay, so we only have to say these 2 cases. The other ones can be reduced to this. So because of this, I will begin studying one, and then I will go to the other. Well, so this is what is called a priori unstable Hamiltonian. This comes from Kierkegaard a long time ago, and I have this in the where epsilon is equal to 0. I already said it, that is I is constant, and so well, the thing is that whatever epsilon is small, we have global stability. And there are a lot of people who call this Arnold diffusion, although this is not legal because, in principle, Arnold diffusion is only supposed to be named for what is called a priori stable case. Okay, so you can begin to complain now. Okay. Anyway, this is very interesting not only for the fact that I'm going to be very constructive, but also to do numerical computations, because numerical computation in the priori stable case, I mean, even today, they are not so easy, but well. Now the point is to show you what are the scattering maps and how to construct them. And we will see that there are some scattering maps, there is an inner map, and so we have some kind of, we can design orbits, okay? I can say, I think that there is an orbit that goes in this way. And then there come the shadowing theorems. The shadowing theorems that we can apply here, the standard case by Ernest von Tichenbardi. I can also, by the way, I'm sorry, but other people that were working in this was, of course, Jean-Pierre. Even Jacques Cresson was also doing several things about this. No? And also, if we know nothing about the inner dynamics, we could even use results about Marian and Rafa and Tere. But the thing is that, as a matter of fact, as I will know a lot what happens in the inner dynamics, typically this could be more suitable, okay? Because these other results, as far as I know, they are better when you know very few about the inner dynamics, no? And you don't need to study what happens in the inner dynamics. In any case, the inner dynamics here will be very simple. Not so simple with 3.5 degrees of freedom, by the way. Good. So let me recall what is this geometrical method. There is a normally hyperbolic invariant manifold. In this case, this I hope that we'll have a picture. This corresponds to the case when P equal to Q equal to 0. So in the saddle point of the pendulum, that is invariant. Okay. And so this is a 3D normally hyperbolic invariant manifold, and it has associated 4D stable and stable invariant manifolds for every epsilon, although for epsilon equal to 0 they coincide, as I will say in a moment, and for epsilon different to 0 they will not coincide, and we will be able to compute them in first order and to look for the intersection. The inner dynamics will mean that we will restrict to this 3D object and to study what happens here. Of course, here there will be no diffusion, and it will be easy to study the of 1.5 degrees of freedom. And the interesting part, at least we are more focused on this, is to study all the scattering map that will all the set of homoclinic orbits going to this set, and to see how many of them we have, and what are the useful, what not, what is the freedom that we have, etc., etc. By the way, you can also complain now because due to the form of the perturbation, the normally hyperbolic invariant manifolds is preserved, but if not, it's not a problem, because if it's not preserved, you can compute up to first order what is the form of this, and all this can be done, okay? Okay, so let's begin with the first case. I recall, imagine now that I have a perturbation G, so maybe let me go to the first slide. Okay, it's a good moment to recall this. Here we have a pendulum, here we have a rotor, here we have something that depends on Q and phi and S, and here we have the f of Q, that is simply this one, and the G phi of S. Now I am assuming that it has this very simple form, that it is it only has this form with the phi and the S that appear totally uncoupled. So in this case, you restrict to the lambda, and although you see here that it seems that this is a Hamiltonian of 1.5 degrees of freedom, is totally false, because when you write the equations, this term does not appear. So this is a totally integrable system that is in fact is a pendulum. So in this case, you have like only one resonance. This will be of size square root of epsilon, and all the ones will be full, totally full. It's integrable. Okay, so there are no holes here. So this is the easy case, and then we will study the other case where there can be some holes. So anyway, what is important in all the inner dynamics is that this dynamics is always, like we say, very horizontal. Okay, even if we have here is full of. I mean, I'm drawing here like the Poincaré map, because I'm not drawing the 3D object, but only like a Poincaré map. So, and because of this, the S is not appearing here. They are almost horizontal lines, and so all these inner dynamics always will be very horizontal. And for instance, maybe it can have some problems here, but what we want to do is to use the scattering map just to go in motions in such a way that the action variable really increases, or simply can do every kind of excursions. In the other case, it is a true Hamiltonian. Recall that the sigma that appears here will be phi minus S. This is a true Hamiltonian of 1.5 degrees of freedom, and because of this, as is a true one, there appear two. If we have two harmonics, they appear only two. So this is a little bit false, okay? there appear two resonances of first order that are the ones that you see clearly here, but there are also other that appear of order epsilon squared, etc., are in the middle. Okay, in the middle there are some chaotic regions that, by the way, are exponentially small, and also there can appear other resonance, but here is also very easy to see that the full space here is filled with invariant tori up to any order in epsilon. Okay, and so this is I'm thinking this when I'm going to apply it later on the shadowing. Anyway, here the dynamics, for instance, is that every time that you are in one of these curves, you continue in this curve. Okay, with some velocity that is of order 1. Anyway, and so it's clear that you restrict here, that it is impossible to have any kind of diffusion, so the I is restricted to, at most, to some motion that is some drift that is of size square root of epsilon. Good. But here we have two resonances. In principle, the idea is if you have more resonance here, more terms here, in first order you will see more resonance zones. Okay. But the point is that only having two, we can prove that there is this diffusion. Good. What about the scattering map? So, I mean, this is a cartoon that I think that it was, as far as I remember, it was drawn by Rafa a long time ago. And so now pretend that the normally hyperbolic invariant manifold is I mean, this is a 3D normally hyperbolic invariant manifold. Okay, and the important thing is that it is hyperbolic. So, I mean, the stable manifold, for instance, here, when you approach, you don't approach to the object, but to a specific. You synchronize with an element in this hyperbolic object, normal hyperbolic object. And if it appears that you have a transversal intersection or a linear intersection, you synchronize in the future and in the past in principle to different points. And so the scattering map is simply the map that goes from x minus to x plus. So this is a very nice picture saying, oh, this is very nice putting this, but this is a local definition always, as we will see. So every time that we have a intersection and a transversal intersection, we have a scattering map that are defined locally. The nice thing is to see here if up to what point there can be global or not, what are the domains, and what happens if we consider different kind of intersections. But okay, so this is what is called the scattering map. And I recall you that here we have an inner dynamics, and we want to see if taking into account this outer map, this scattering map, it is possible to go back to another point and to gain action in this way. Good. The good thing is that, well, it's symplectic, but only this is, in fact, it's exact symplectic. Okay, yes, but not only this, but it has a formula, and this is a good thing for us because the formula says that the scattering map in the variables of the lambda tilde takes this form, and in this form, look, here you see there is some I and phi, and I'm putting here some theta. First thing, this theta is nothing but phi minus is, that this kind of first integral in the inner dynamics. Okay, so I will come back to this in a moment. And so it depends indeed on this variable theta, and it has there is some L star that is a reduced Poincare function that I will introduce in a moment. So I'm putting now only what is the shape of the formula, just to tell you that according to this, the scattering map is just the minus epsilon time flow of this Hamiltonian. Okay, so this means that it will be very important to compute this strange, for the moment, function that is called the reduced Poincare function, because for any of these reduced Poincare function, we will have a scattering map, and so to study what are the orbits under the scattering map, as this will be a Hamiltonian of 1 degree of freedom that will be integrable, because this will be Hamiltonian will be the first integral, we only have to draw, in this case, the level curve of this function, and this will tell us which are the trajectories that are followed by the scattering map. This will be different, by the way, when we consider more degrees of freedom, because in that case, this will be a first integral, but this will be not an integral system, and so you have to work more. Okay, and this is what we're trying to do now. But in the case of 2.5 degrees of freedom, or in the case where this I is one dimensional and also the theta, is very easy, because the point is that we will look for this strange, for the moment, formula and for the domain, and so we'll be drawing level sets of this L star, and with this we can try to design what are the orbits that diffuse. Okay, so this is very important, so to compute this. This is the point. Another important thing is that in principle this is a function from I phi s to I phi s, but in s is trivial because it's constant. So it is not a 3 to 3. It's a 2 to 2. It's a real symplectic, because what is a symplectic when you have three dimensions? It's symplectic because you can forget about ds. And ds plays the role of a parameter. As it is a parameter, in principle, there are an infinite number of symplectic scattering maps. But we will see that, well, in the end, only playing with two values is enough. Okay, but I will come to this. And the important thing is, if at any moment I draw some phase portrait or the level curve of this, the scattering map only jumps like make jumps of the order of epsilon in all these level curves. Okay, so now the problem is to look for this kind of strange function that is a reduced Poincare function. What is this? To this, this is very related to the Malikov potential or to the intersection of the invariant manifolds. What is the way to look for invariant manifolds which intersect? I mean, in general, you have a vector, but in Hamiltonian, you know that everything in Hamiltonian comes from only one function, the Hamiltonian one function. Every change that you do, you have one generative function, and when you compute the intersection, you have one function that is called, for instance, Malikov potential. That is, in this case, well, it has an in this case it has an explicit form that is simply, this is like the motion along the separatrix. There was a separatrix that will say something in the next slide, minus the motion on the lambda tilde. But anyway, it has exactly this formula, and I will tell you something about this in a moment. But there is a result that says, okay, if I am able to compute this Malikov potential, and I will be able to do this, and then for any I phi s arbitrary in here, if for every critical point of this function, now look, L is restricted, so this is a Malikov potential, but L is restricted to the unperturbed inner motion. Okay, for any critical point not degenerate that I find, I will be able to prove that there exists a traversal homoclinic point to lambda tilde epsilon and with that is close to some part of the separatrix. Okay, so this is important because look, this function that appears here, depending on I, this can be periodic or quasi-periodic. By the way, look, this is a function, a real function. One can check that if I is rational, this is periodic, and if I is irrational, this is quasi-periodic. Okay, so if it is quasi-periodic, it has an infinite number of not degenerate points in general. Okay, but for practical purposes, maybe not all of them are very useful, because if you spend a long time going outside before coming back, for practical purposes they are not so interesting as the first or closest maximum minimum. Okay, and in principle we are going to consider the closest ones. So indeed this means that if in this Malikov potential there will appear of maxima, minima, and typically will be non-degenerate, and this is what we are going to study in this case. Okay. But we have a tool. And in our case, in our model, well, this was a pendulum, so we have a concrete separatrix. And so I can put exactly what is the formula of the Malikov potential. And look, the Malikov potential always has the same harmonics as the perturbation. So it is like convolution, it is a kind of convolution process. So if the perturbation dg was this, the Malikov potential exactly is the same one, but with this coefficient multiplying by some function of I, although in this case it does not depend on I. But it has exactly the same harmonics. Also in this case, okay, when I have the other case, when instead of S I have here sigma, I have the same form for the Malikov potential, although this A2 is a little bit different, okay? And so you can get this simply computing by residuals, the integrals that appear. And so, look, what is important is that what I'm going to do now is try to see what happens along some straight lines. I recall what I have here. So I was telling you, look, if you look about some straight lines, every maximum or minimum that I have will produce me, as long as it is not zero, will produce me a transversal homoclinic point. So we have to, first of all, to see what is the behavior of this Malikov potential. And for instance, let me put in the Malikov potential that I have, in this case, for some value of mu, and some value of I, and for the G phi s that I recall there was this very simple. And come on, and this is very simple in this case. Look, I have, for fixing I have a function on the two torus with only two harmonics. And so this is the easiest case because it will have a maximum, a minimum, and two saddle points. If I consider more harmonics, okay, it will be more fun, will be more critical points, etc., that can be computed. But the point is that only in this simpler case, and this is kind of a generic case because we have what happens with more theory, we will have 4 critical points, and 2 of them will be one maximum, one minimum, and 2 saddle points. For instance, this is what we have in the case of we have here a minimum, here a maximum, and in between there is here a saddle point, another one here. Okay, and typically, and this is the generic situation that we will use in a moment. Typically, these 2 saddle points are not in the same height. Okay, height. Good. Finally, what is this kind of reduced Poincare function? Well, reduced Poincare function is simply so that as we know, maybe for every time that maybe if we know what is this tau star that I will recall in a moment, we simply evaluate the L star on this, and it happens to be that this depends really not in an arbitrary way in the variables I, phi, and s, but it depends just on this theta. So let me recall what is this tau star. Let me try to explain you first in a graphical way and then with formulas. The idea is that now, imagine that I am here, so you are now in the middle of, I don't know, in the middle of the mountains. Here there is a valley, and here there is a mountain, okay? And you want to travel in some straight line that somebody tell you, look, go through a straight line, okay? And depending on I, you have different slopes. So it is very clear that, for instance, if you are already at the top of the mountain or here in the valley, you already begin with a maximum or minimum of the Malikov potential, and you, in this case, you will be in also the point of your path. But if you are in any other point, typically you will be going here and there, and from time to time you will arrive into this kind of basin of the valley, so you will be approaching this, so you will pass through a minimum, and when you go close to the mountain you will pass through a maximum, etc., etc. So depending on the fact that this slope is rational or irrational, you can have an infinite number of minima and maxima, or you can have a finite number of them. You see? So these are the problem, and the thing is that the tau star is simply that you parameterize this line at every time that you pass through a maximum or minimum. In this parameter tau, the tau star will be simply the value of the parameter. So in principle, this is the main important thing that we'll have to do, is to study which is the possible tau star that can appear. Okay? And so this is very important because to understand what happens, we have to study what is this tower star, so we have to check when we are able to pass through a minimum, maximum. So now I come back before. Now imagine that, look, typically imagine that you have to pass from here to there. No, you have some mountains there. And when you pass through a mountain, okay, at some moment, independently of the line that you put, at some moment you will arrive to a maximum. Okay? But this maximum will depend on the direction that you have. And this kind of maximums, in this way, you look at mountains, this is what we call the crests. Okay? So, no, I mean, typically, if you are clever enough, the standard thing is to pass always by this minimum, but if you are going through any kind of directions, every time that you pass to one of these crests, you will have a maximum. So what we're going to do is to study this kind of different crests that can happen. And this will be related to some properties of the Malikov potential. So again, we have to look for these tau stars in such a way that they satisfy this equation, and there are different viewpoints. Simply, the first one that I was telling you is, okay, let's draw different straight lines, and for every straight line, let us look for the maximum minimum, or we are going to look exactly to first look for the crest that will depend on the slope that you have, and every time that I touch this crest, I will be in a maximum or a minimum. And so this is the main point that we're going to do, to study the crest. So, and in this crest, they are characterized for the fact that this tau star will be equal to 0. So let me do this. I will make a picture in a moment. Maybe I will put the picture and then I will define this. So this is the level curve for the Malikov potential that I had before. So recall that I had a valley here. I have a minimum here. At some moment there appear a saddle point that is here. Okay. So I continue. At some moment appear the other saddle point, and there appear the maximum. And now imagine that I throw this line here, or some line here that goes there in this way, etc., etc. And I'm traveling along these dotted lines, and I want to see which are the minimum, maximum of when I travel along them. And so the point is that, for instance, if I am here, when I touch here this crest, I will have a minimum. If I continue there, the next time that I touch this other crest, I will have a maximum, and so I continue, etc., etc. So every time that I touch one of these two crests, that they correspond to the unique curve when I have that satisfy this equation, and these crests they begin close to this maxima or minima. So this would be, for instance, in this case, this will be a crest corresponding to a maximum. This one, because here there was a maximum, there will be another crest will correspond to a minimum. At least in this case, we will see that the main problem here is to study what is the bifurcation of this crest. But every time that we know what is the behavior of the crest, it will be very easy for us to look for homoclinic points, no? Because every time that I touch the crest, I will have one homoclinic. So in this case, you see that we have a lot of possibilities to play with. So let me recall what is the definition of the crest that they have. I mean, simply is the curve that satisfies this equation. But these equations are very simple in our case, because I recall you that these L's, they had only two harmonics, so they have this expression in the first perturbation of this other expression. So when you want this, when you want to solve this, come on, you can solve, for instance, here sinus of S as a function of sinus of phi if this is smaller than 1, or if this is greater than 1, you pass this to the other part. No? And so when we're going to draw this, we will speak about horizontal or vertical crest, and this will depend on the fact that the S can be isolated as a function of phi, or on the contrary, the phi can be isolated as a function of S. But this only depends on the value of this mu alpha I. I recall that the mu was simply the quotient of the coefficients, and the alpha of I has this expression. Okay, so all this totally computable. And so it is very important to say that the critical points of the Malikov potential, the maximum, minimum, the two saddles, they always belong to one of these two crisps. And another way of looking at this reduced Poincare function is that the reduced Poincare function is nothing but the Malikov potential evaluated just on this crest. So look, this crest that I'm calling the C of I, you will see that a lot of times this has two components, and this is the standard case. But this is what we have to study. Good. So let's try to study this. And so we are going to study what is the behavior. Now I begin with playing with the parameter. There was this mu that I recall this was the quotient between the A1 and A2. And so if this mu is small compared with alpha of I, so in the previous equation I can put S as R sinus of phi and have two possibilities. And so here these are the two possibilities when mu is between 0 and 0.97, that here there is a crest that it passes through the maximum of the Malikov potential, and here there is another crest that passes through the minimum of the Malikov potential that are here. And so let me call it this way. I will call horizontal because in this picture phi and S, and so this should be, there is a phi here and S, they look like horizontal because I can isolate S as a function of phi, so they are clearly curves defined for all values of phi. We will see that this will change. And now throw lines. Another thing is that I don't know if these lines will touch in a traversal way or not, and this is the other thing that I have to study. I do this, and for instance, now if I restrict a little bit more, if mu is now between 0 and 0.625, every of these lines, this is what we call the limb line. The limb line is the line that follows the unperturbed inner dynamics. We have to see now if it touches in a traversal way. So this happens, and this is easy to check, when the mu is a little bit smaller, something like this, and in this way we always have a traversal intersection. So this means that every of these, every line that we consider here always touches once to this crest, another to this crest. So we have two global scattering maps. One will correspond to the maximum crest, another to a minimum one. And so these are the level curve of this reduced Poincare map function. So look, in the first case for the maximum one, we see that well, I mean, these are level curves. We see that here, the idea, recall, if I am here, I will be jumping. If I will be following only the scattering map, like making jumps of order epsilon, so if I will restrict only to a scattering map here, and I forget about the inner map, I will, at some moment, I will have a maximum diffusion, and that's all. But there is something very special, because there is one line that I will come back to this later, where it appears that, oh, come on, this is the best one to have kind of diffusion, because it is telling me that I will be able to follow only this scattering map, maybe combined with the inner, to go to escape. Okay? So I will study this. And if you look at the minimal one, there is like it's kind of mess, no? Because it is not so clear here that this will be faster or not. Anyway, this is something that has to be studied. You don't have to only look at the figures, but because one thing is to say this is clear from a geometrical point of view that you see something more vertical, but when you take into account the times, it appears that they are more or less equivalent. But anyway, in this case, it appears to be easier to follow this scattering map. There are other more possibilities, but in this case, this is very clean, and using only this plus the inner dynamics, we can prove the stability. If, by the way, something that we don't know, only using the scattering map, we see we have diffusion. Okay? As I am working only with a scattering map and not with separatist map, and I have to use shadowing, I cannot say, well, look, only with the scattering map I will have diffusion, unless that I apply other results. Okay? that maybe, and in this will be the case, that maybe I can apply the results by Tere, Marian, and Rafa. Only using a scattering map, you will have diffusion. Another thing is the time that you spend doing this, and as later on I want to compute times, I will use this combined with the inner map to give an estimation of time, because the other problem is that when you don't know nothing about the inner dynamics, you cannot give estimates for time. Good. So we already did this in this case, and for the first case, when the mu is greater, than this 0.625, well, it appears that the slope is smaller, and so at some moment there appear some tangencies, and so you see that at some moment there appear bifurcation of a scattering map. So in this case, this line touches 3 times this crest. So instead of one scattering map, we have like three possibilities in some parts, only some small parts. Okay, and so this means that in this case, when I make the drawing, there is some. It's almost very similar to the previous one because it was done for. Oh, I didn't put here the mu. The mu here was 0.8. I'm sorry. No, it's here. Mu equals 0.9. So everything is very similar, except that there is some part here where there is like more fun, no? And it's true because when you arrive here, you have like 3 possibilities to continue. Well, indeed, this was done in this way. You arrive here, you can continue with the same scattering map, and then here it breaks, or you can use the other 2 scattering maps. And so it's a matter of if you somebody tells you, I want to pass just through here because I have to make some contact here, etc. So you will have to compute more. But if you only are now, you only want to make diffusions, you forget about this, and you simply continue with your favorite line here. No, so this is a matter of, as we are only considering here just to drift, and we don't want to pass through a specific. We are not taking too much attention, although it is not a problem to do this. Okay, here the only thing is that you have to decide which is the scattering map that is more convenient for you. The good thing is, this is very constructive. Okay, so what happens now if mu is greater than 0.97? Oh, these crests that were in before horizontal, now they are vertical. Indeed, now they are. You can have to look at this. They are connected in a different way, and so it happens that sometimes the scattering map is not well defined. So they were in all the whole space, so as it happened in the previous case. So in this case, what we have is that, well, there is some green part where the scattering map is not defined. Okay, so you want to pass through this part with this scattering map. This is not possible, so we have to use other ones. Okay, again. And here also we have a problem because this nice highway, so now it has some problems, and so we have to do other things. Okay, but no problem because you can use the other part. So now let me illustrate this with a concrete case. No, let me first speak about the highway. What are these highways? In this case, the highways are some concrete curves that they are associated to a level curve, that is these ones, that they are always vertical. Okay, and when mu is small, they are all for all values. If mu is not so small, as happened here, they are not. They are not defined everywhere, and so here there are some parts where these highways are not defined. So all this depends on the parameter. Okay, but these are the parts where, in principle, diffusion is faster. So I recall in the first case. There are highways, and when the mu was smaller, in this case, for instance, from mu equal to 0.6, there is I mean, if I have to design a path to escape, for instance, let me try to choose this one. And as I will choose this one, I will be able to give concrete estimates for time. Okay? If I choose another ones, I have to change estimates, but this is not a problem, as I will tell you in a moment. So the scattering map is doing this in this way. Okay? Take into account that this highway is unstable here, so typically you will be a little bit out, and you will need the inner map to come back to here and to continue this. So this means that when I need to compute estimates, I will have to compare the time under the scattering map and the inner time. And in the cases that I am computing here, always the scattering, when you follow the scattering map, it takes more time because I arrive to a distance that is of order log of epsilon. And so, for instance, this is the once you have this, you can design now the diffusion path. No? For instance, here there is I already put this this level curve of the reduced Poincare function some slides before, but now I'm adding the red ones is the inner map. So I'm combining here the scattering map that is not defined in the green parts with the inner part that defines everything and has this red dot. So for instance, imagine that I begin here. So what I will do is I will continue in this way, okay, no problem, I'm adding energy. And here, oh, I have a problem. So maybe as I have a problem, at some moment I switch here to the inner map. When I switch to the inner map, I come back here, and then I say, well, now I can recover again the scattering map. I can arrive here. Oh, here, this is I have some problems here with the scattering map here. I go again with the inner map. Okay, so now, for instance, I go here, and so oh, I can jump up to this part. Okay, and so even I can go here, and then, if necessary, I take again the inner map. I go there. I can take again the inner map. I go there. And then from this moment on, I can continue with this scattering map. Okay, this is one possibility. You have plenty of possibilities of choosing the path, and although it is intuitively it's something very curious because the ones that sometimes you choose are not the ones that give you the optimal time, but this is something that has to be checked because, as you know very well, when you have the phase space, it is not telling you how fast are you going. Okay, because the velocity is something that is not drawing here. What about the time of diffusion, for instance? And about the epsilon that I forgot. Well, in the case that we are following one of these highways, we have a formula that is this one. So the time of diffusion has this form. It depends on some Ts over epsilon, and we have here a 2 log of C over epsilon. So here there appear two constants, okay? And here this is dependent on epsilon. Before speaking about the constants, the time of diffusion in this a priori unstable case is of this order. And this is something that agrees with all previous estimates. The nice thing here is that you can put even, in this case, what are the constants. What are the constants? How I was able to compute these constants? Because I was looking for the inner dynamics, for the scattering map, I was looking for the differential equation that I had there, so I was able to compute what was the time that I was following the scattering map. I was able to give these estimates here because I was computing only the contribution of the scattering map, and because I was checking that the time spent under the inner map was smaller. And in this way, I can at least tell you, look, at least for this time, there are orbits which diffuse, okay? If you tell me to follow other orbits, this can change, but this can be also computed. Because I was choosing specific trajectories in the inner map. This concerning time. By the way, I didn't say something in the theorem that appeared. Let me tell you something at the beginning of all. Some epsilon here. What about the epsilon? How small is epsilon? Okay? The epsilon, it depends, and this is not written. I didn't know that I had to speak at 11, so let me tell you how to compute this epsilon. So look, in the scattering map that I have here like a first order and an error. This formula is good as far as these derivatives are greater than epsilon. I need epsilon to be smaller than derivative, so I have to have an estimate of this L star. But this L star is very related to the Malikov potential that appears here, and the Malikov potential you see here. for instance, in this case or in the other, that this Malikov potential, this coefficient is exponentially small with respect to I. So if I is very big, this will be exponentially small. So this epsilon will be linear with respect to, it will depend essentially on A1, or will be exponentially small with respect to the I star. So you want to go with I star that is very large, it will take you a long time to do this. Okay, and this is something also that this is something that we check numerically. Good, but so the good thing is that this is computed. Just to finish, let me tell you what are the main differences when I consider the other perturbation. Okay, so I will, in this case, there are no global highways. It's a little bit more complicated. The creases are not always horizontal or vertical. So at some moment, depending on the parameter, they are horizontal, they change to vertical. So it's not so easy to have global scattering maps, and so there are always multiple scattering maps. Okay, I can explain you the details, but I think it's better to tell you what how I can get all the scattering maps. Well, now I have to change from the space of phi s to a space of sigma that appear here. And so if I do all these computations, it appears that the intersection of the nim lines with the crest, they begin in the diagonal in the plane phi and sigma. And so this means the following. So let me go to tell you the idea, the main idea. This is the sigma phi set. Okay, here, for instance, in this case, for mu that is small, that is what's written here. Imagine that these are the creases. So I'm writing here this and this and this. And so the point is that for every this is the diagonal when sigma is equal to here to phi, and to get a scattering map, I simply in this first case I'm throwing down lines, and when I touch this crest, I can draw a scattering map, and this is what was done here. Okay, and this is the first time that instead of putting arrows, I'm putting now orientation. Every time that appears a red, means that the I decreases. So this is telling you that this line goes in this way, and every time that this a green line, the I increases. No, and so this is equivalent to putting arrows, but this is more economical from for drawing. Okay, so this could be a bad scattering map to grow I, because I will be almost all the time going down, because I'm touching, for this diagonal, I'm touching this green line here. So other possibilities. Okay, let's go up. Instead of touching this crease here, we touch in the upper part. Okay, and when I do this, I have more green. So following the scattering map, I have a lot of zones when it increases. But I have also other part where it does not work very well. But other possibilities. Okay, we can say, let me half of the trajectory is going down and the other going up, and let's see what happens. And in this case, I have all this part, this nice part, where this is going up and this is going down. Okay, but I'm not doing the things in a good way, because there is another crease. Maybe it's better, depending on which part of the diagonal I am, that to choose this other crease, and this is the best thing. If I do this, for instance, for the diagonal, if I am closer to this part, I simply go to the closer always crease, and here there, I get this scattering map. That, by the way, this is a piecewise smooth scattering map. So there are here these two lines, they are singularities. So here it is like this one scattering map, this is another one, this is another one. So I put this all together. So this is a piecewise. There are three scattering maps here. Okay, but the nice thing is that, well, when you arrive here, well, you're in a trouble when you arrive there, no? No, I am going here, and I'm going there, no? And so what I do here, no? By the way, this is something that appears in the piecewise smooth systems, and this is what is something that is called. There is some Filipov flow that asserts that maybe you can consider following now in this direction. So forget about the differential equation. I can tell you that this is a new motion, no? And so during a long time, people have been saying, well, this is very nice, but I don't believe this, etc., etc. But it happens that in the cases that we're working, we have seen that this corresponds to maybe to what happens in reality. So this would give more support to this Filipov business. And also, this would give more support to the fact that maybe this is the substitute for the highways in this case, and this is the fastest part of diffusion. Although this is something that now we have to work. Okay? But anyway, the conclusion is it's good to have scattering maps that are piecewise smooth because you choose whatever you need. And in this case, look, what I'm going to do at this moment is to use the inner map to come back here, to be very conservative and to follow what is known. But it appears that maybe in the future we'll be able to go along this. But I don't know if this will be possible or not. I'm only saying, look, this appears to be something interesting. To finish, in the 3.5 degrees of freedom, that could be this case. So now imagine that you have like one pendulum but two actions of this kind, okay, with two different omegas that can be positive or negative, whatever, but different from zero. So I have 3 harmonics in this case. I need 3 harmonics also. So the kind of result that we can have in the easiest case is that when this A1 and A2 over A3 is small, we are almost in a similar case to the first one, and one can prove results like these ones, that for any I minus and any I plus and any delta, you can be close to this I minus and later on to this I plus, and that's all. I'm not saying a lot of things, but a lot of things I'm not saying here is that there are double resonance in between, okay? But I will not be able to say anything about this, and because of this, I need some delta here to avoid, if necessary, multiple resonances. Okay? This is what is here. But this can be also computed at least for this value of the parameters. So you can also now decrease our surfaces. And here in these very nice cases, there are 2 horizontal surfaces, and so you only have to look. You can construct 2 very nice scattering maps. And there is one that is the one associated to this maximum crest. Okay. And so instead of doing this, in this case, you can also put an arbitrary path, and you can follow this path at a distance if you put also the delta in a very similar way to what we did with Rafa and Terry in a paper about the cases where you have 3 or more degrees of freedom. This is also possible in this case, but the nice thing, another thing is that also in this case, we follow the nomenclature introduced by Jean-Pierre. We're speaking about polyscattering map, that using 3 different scattering maps, we can go from one to another. But I don't have time to speak about this. Also, there are highways because I don't have time. But there are also highways in this case, and these are Lagrangian manifolds that are not bounded, and you can have the equations for them, and also, but they are not integrable, and so what we don't know at this moment if these are the fastest or no path of diffusion, because this relies on numerical experiments that we have begun to do with Albergranados, and so we are now looking if this is the fastest way or not. But now if we only want to prove diffusion, we can do this, but we want to study more what is what is the inner map, and to see how to combine this with the scattering map. Okay, and well, this is more. Probably you have a lot of questions. Fortunately or unfortunately, I will be here the rest of the week, and I can be more specific on a lot of things. Okay, because I had to speak only for 1 hour. Okay, thank you very much.